product measures. Okay, so it was kind of vaguely mentioned once, but we haven't actually done it. So let us do it now. So what is product measure? So the problem is very straightforward. Let me state the question that we want to address. So we have two measure spaces. Okay, two measure spaces. So what will happen in case I forget to tell it later? So we shall always assume, mu and nu finite, and everything generalizes to mu nu sigma finite. Okay, so everything, I mean, so you remember last time how Radon-Nikodym theorem proof was reduced from the sigma finite case to finite case. Whenever that is the usual way, I mean, if things are sigma finite, you break it into pieces. X you write as a disjoint union of, you make a measurable partition such that x1, x2, xn, etc. are a partition of x, so that on each xn itself is a finite measure space if you restrict mu to xn. So that way you get it as a disjoint union of finite measure spaces, and same for y. And then you can put together, if you have done everything for finite measures, then you can put that together to get it for sigma finite measures. Okay, so actually it's a good question whether sigma finiteness is essential. I believe it is, though I cannot give you an example, a counter example otherwise. So let's work with this. This is good enough for our purposes. But is this the max you can go, or can you do away with sigma finite assumption? Is something I should have known, but I don't know now. Okay. What is it that we want? So we want to build a new space, namely, like you have done in many courses, and this is a natural and important construction. So when you have vector spaces, you build a product of vector spaces, right? I mean, there are different products. There's tensor product, there's or there's direct sum. So let's say tensor product. Like that, you have products of groups, topological spaces, you have products of topological spaces. So it's a product structure that we want to build. So at the set level, it is going to be simple. At the set level, what we want is, so what do we want? So we take the set level, we want Z, we will take Z to be X Cartesian product Y. Okay, so this is all pair tuples of X comma Y. Okay, so now I want to, do I have a measure structure on this? If I look at H, it is just a definition. Okay, so this is, I will write like this. So this is just, don't think that, I mean, this is something that I have defined before. No, it's just something I'm defining now. It is the notation for what I'm going to define. It is a sigma algebra on H. What is a natural sigma algebra on H? I have the sigma algebras on X and Y. What is the natural sigma algebra on H? So it is, what I certainly want is, I want all sets of the form A cross B, where A is a measurable set in X and B is a measurable set in Y. Okay, I would certainly want all of them to be measurable. Okay, so products rectangles have to be measurable, but this will not give a sigma algebra. You take the smallest sigma algebra containing all rectangles. So the sigma algebra generated by, so this is sometimes called cylinder sigma algebra or product sigma algebra. So why cylinder sigma algebra? Because this is also the sigma algebra generated by, you can take A cos y, A in F, you can take these special types of rectangles which are called cylinders. So if you think of X is here, if we draw X, let's imagine the picture I'm drawing is when X and Y are both copies of R. So what is A cos B? A cos B would look like a rectangle. Okay, A cos B is, if I take a set A, let's say A is this set and B is a set on this side in Y, then we know A cos B is this rectangle. So this is the product set, and so we call it product sigma algebra because it is generated by all those rectangles. But if you look at A cos Y, what is A cos Y? A cos Y will be a set like this. B is replaced by the entirety of Y, so A cos Y is this thing which looks like a cylinder, right? If you were to do it in R2 cos R, it would look like a cylinder. You think of this as a cylinder. This is a cylinder. The other cylinder is y x cos b. We also want cylinders that go in the other direction. So like this. So this is a cylinder also. So these are cylinder sets. So this thing is called cylinder sigma algebra. It's clear that these two are the same, right? Because of course every A cos Y is of the form A cos B, X cos B is of the form A cos B. So these sets are rectangles. So this sigma algebra is contained in the top one. On the other hand, A cos B is just the intersection of these two. If you see this picture, this rectangle is the intersection of those two cylinders. So all rectangles will be actually there in the sigma algebra generated. Rectangles are not cylinders, but they are intersections of cylinders. So this is called cylinder sigma algebra or product sigma algebra. Usually, I think in probability, this language is used, cylinder sigma algebra. I'm not sure if any analysts use it, so you can call it product sigma algebra. So the question is, so these two are clear. The measure structure is clear. So what is not clear is what is the measure. What we want is measure, say denoted, we can call it the product of mu and nu. Okay, this is just a notation. Okay, so we want a measure on H such that at least for rectangles, I want it to be this. So if it exists, so does it exist? So is it unique? If yes, we call it the product measure. Of course, it's the product of mu and nu. Yeah, it's the product measure and it's the product of mu and nu. Okay, so that's what it is. It is not so obvious how to define this. See, I mean, defining the Cartesian product we understand, and this one was easy. But what I know is that how the measure should be on some collection of sets in the sigma algebra, namely rectangles. But does that mean that I can extend it to the entire sigma algebra? This looks exactly like the kind of extension theorem type question that one should be what we were addressing. We have it on a sub collection and then whether you can do it. So that is one way to go. We will do it slightly differently. And because it's not only that we want to do this, we want to also understand how integration with respect to the product measure behaves. So that is called Fubini's theorem. Okay. So that will be the other objective. Hopefully we will complete all of it in this lecture. So one approach, which is not the approach I will take. So let A be the algebra generated by rectangles. And just like in many other situations, you see this is actually a pi system. If you take a rectangle like this, so I mean, okay, so now just think of this rectangle. The thing is, intersections of rectangles are rectangles. So if I take some other rectangle like this, the intersection will be a rectangle also. That is one thing. So it is what is called a pi system. If you remember, pi system is a collection of sets which is closed under intersections. So rectangles are closed under intersections. Not only that, if you take the complement of a rectangle, so maybe that picture is overcrowded, so let me draw it here. If you take the complement of a rectangle, so let's say we have a rectangle like this. So the complement of this rectangle is actually can be written as a union of rectangles, right? So because what is the complement of this? It's everything outside, which is a union of one rectangle like this, another rectangle like this, another rectangle like this, and so on. So how many are there? I think there are 8 rectangles. Okay. So there is one rectangle like this, and so on. So it is a union of all these other rectangles. Therefore, the algebra generated by these rectangles is just the collection of finite disjoint unions of rectangles. So it's actually, so you can write this algebra as collection of disjoint finite unions of rectangles. Okay, so that is what the algebra is. So on that, so it is kind of clear how to define it, right? So what you want is mu you want to be. So we want only one possible way to define it. So define, let's not call it mu, let's give it some name, some other name, which I don't use. So define theta on the algebra as theta of R1 union. If I have a union of rectangles, I want it to be theta of R1 plus theta of Rk, where if the rectangle is Aj cos Bj, then theta of Rj, it is whatever I want it to be, mu of Aj, nu of Bj. There is no other choice. So that's how you would define the measure on the algebra. And then the key thing is check countable additivity of theta on the algebra. Okay, so conclude. theta extends uniquely to the sigma algebra H. Because it is also uniquely because H is generated by the algebra, and on the algebra there is no choice. So if there are two possible measures, they have to agree on the algebra A, not just on rectangles, but on the entire algebra. Therefore, they have to agree on the sigma algebra. So this would be one natural approach. Of course, where is the key step? The key step is here. Check the countable additivity. This is the key step where you have to do the work. Other things are there is no work involved. So this is the point you have to check. Countable additivity on this means suppose an algebra element is actually a countable disjoint union, pairwise disjoint union of other algebra elements, then you have to see that the measure you have specified is the sum of the measures. So that's the part which requires checking. And we had given some things that make your life easier in this checking using these compact classes and stuff like that. So I will, anyway, this is one natural approach that we will not take. But many books may do it like this. So, for example, you can look at Bogachev's book. Okay, Bogachev's book does it like this. Many books do it, I think. Many books just do it like this. We shall take a slightly different approach, use some things that we have already done about integration, measures, and so on. So it's a bit easier, and as you know, this is kind of boring, and this checking can be a little annoying. It's not like super hard work or something, but it requires work. But we will do it in a slightly different way. Here I'm following a different approach. So so this is one of the books I have mentioned is Kahn's measure theory. It's a kind of short book. It is, I don't know, it is not maybe a famous book, but I just found it one day, sometime in the library someday. I mean, last time I was teaching, and I found it to be a rather efficiently written book. It is not too big and it's nice. So this one is nicely done there. So what I'm presenting is that approach is there. Okay. So we will do it like that. Okay. So what is the approach? So let's recall again. The problem is we have two measure spaces which are assuming finite. And then we have the product, Cartesian product Z and the product sigma algebra F10, we'll read it as F product G or F tensor G. And we want a measure on this H. So how do we do that? So we need to do a few preliminary things. So some preliminary things. So let's write down the setting here. So we have xf mu, yg nu, and zh. The question is what to put there. Okay, and these are finite measure spaces. And z is x Cartesian product y, and h is the product sigma algebra, which is the sigma algebra generated by rectangles. So what is this measure that we have to put? So that is where, but so here is some preliminary work we will do. Okay. So let's do some preparation. So let me state. So let me make a definition. So,
sir.
Yes. Go ahead.
I may have missed this initially, but when we say rectangles here,
yeah,
or for that matter, rectangle necessarily requires some form of interval, right? What are our
No,
intervals
no,
here?
no, no. No, not necessarily. Here, these are kind of rectangles in a generalized sense. Any
Right,
set in the sigma algebra F times any set in the sigma algebra Y,
right, okay.
I call it
So,
rectangle. So, for example, in R2, here,
uh
if it was R2, R cross R, if X and Y were both R and F and G were, let's say, Boyle sigma algebra, then you would have very general sets like Q cross Q, for example, would be a rectangle.
right, right,
Q
right.
cross Cantor set would be a rectangle. So you can take any two Boyle sets, take their product. So that would be, I am calling it rectangle now.
Okay, okay, got it, sir.
It may not agree with the general notion of rectangle in R2, but here that is I don't have a notion of intervals. Sometimes what you say is true actually. Sometimes this F may have arisen from some algebra and this G may have arisen from some algebra.
That is
Then
precisely what I was thinking. Elements of those algebra.
yeah, but no, that's not necessary. Here, I just let's not complicate things. It's not needed and not necessary for us here. So it's just any product of anything that is of the product form is going to be measured. So sets which there are sets which are not of that form, of course. For example, the disk. So it doesn't matter what you do. If you take R2 and you take a disk, it cannot be written as a product of two sets. Okay. So that is sort of clear, right? So, okay. So that's the, any other questions? Yeah. Okay, if not, so let me make a couple of quick definitions. So for a set contained in the product space Z, the Cartesian product, define two sets. I call it Ex dot. Some people put X below Y. Let's just do it like this. Ex dot is the set of all Y in capital Y such that X comma Y belongs to E. And E dot Y is the set of all X in capital X such that X comma Y belongs to E. Okay, so what is it actually? So if you take a set here, so let's say your E is some set like this. Then if I take a particular X, so if I take this X, this is X, let's say X1, then you look at all those Y for which X1 comma Y belongs to E. So that is, and then you take that set in Y. So, okay, so, well, you should transfer it to the Y. So this is, but just, I hope it is okay if I call it EX1. EX1 is not a subset of the product space. It is a subset of Y. What I mean is you take all those things and then project it to Y. So really EX1 is here. Okay, so maybe, yeah, let's not confuse things. EX1 is a subset. It is those parts. So you take X1 and all the parts it cuts through. On the other hand, if your X was not this, but here, if this is the X I take, then EX consists of two parts here, this as well as this. I mean, well, that is the parts which are there. So when I project, I get something here and a little bit here. The union of those two sets was what will give me EX. On the other hand, if you take something outside here, then EX is empty. Nothing, there's no Y for which XY belongs. So that is what this is. And similarly, E dot Y, I mean, so the dot is to indicate, because if I just write E2, then it's not clear whether I'm taking sections like this or sections like this, because E dot Y does the same thing except it fixes the Y coordinate. So in E dot Y, we fix the Y coordinate and look at it like this and then project it to the X part. Okay. So this is E dot Y. So like that. So EX dot is always a subset of Y. Okay, so for x in x, capital X, and this is a subset of x for y in capital Y. Okay, so the dot tells you which coordinate is being fixed. Okay, so the dot is the free coordinate. So it's 4 o'clock, and so the second one is being fixed here, the first one is being fixed here. So these are called sections. The term used is sections of the horizontal section. So these are vertical sections, these are horizontal sections. Okay, so you can call it that. So this is what is done. Similarly, for functions also you can do this. For f from z to, you can take it to any space, but just let me take the usual extended real numbers. Define fx dot is a function from y to r bar, and similarly f dot y will be a function from x to r bar, where of course x is in x, y is in y. So if I fix an x in capital X, fx dot is a function on y defined as fx dot of y is f of x comma y, and fy dot of x, f dot y of x is defined as f of x comma y. So this is a function on y, this is a function on x. So these are sections of the function. These are also called sections of f. So and the usual thing happens. So it's an easy point that I will leave you to check. If f is the indicator of a set in the product set, then fx dot is nothing but indicator of ex dot, and f dot y will be the indicator of e dot y. Okay, sections of the functions will be just the indicators of the sections. Okay, so that's what it is. Is this clear? So these are the sections. So this will be important because I mean, so the simplest is, so this, well, we will see. I mean, I don't need to give examples. So let me state the main preparatory lemma that I want to say. And once we do that, then it will become somewhat smooth sailing. So as before, all the setting is as above. Suppose, okay, so first statement, if E is a measurable set in the product sigma algebra, then Ex dot is a subset of y, right? The section, it's the vertical section, is a subset of y. It belongs to G for all x in capital X, and the analogous statement is that the horizontal sections E dot y belongs to F for all y in capital Y. Okay, so this is true. So if you take a set and then its sections belong to the original sigma algebras. So that is one statement. So the corresponding statement for functions is measurable. So let's take the Boyle sigma algebra here and H of course here. Of course that's what is meant. Then f x dot is a function from y to r bar, right? It's a function from y to the extended real numbers, is measurable with this. And so is f dot y, which is a function from x to r bar. Of course, the sigma algebra now is f and Boyle sigma algebra. So sections of measurable sets are measurable. Sections of measurable functions on the product space are measurable. That's all. Okay. So second, further, next I want to say further things. Is this statements, are the statements clear? So just sections of, I'm not saying the other way. By the way, the converse is not true. If sections are measurable, it is not at all true that the set is measurable. I'll maybe give you an example. Uh, so maybe I tell you that the converse is not true. So if you take with the Lebesgue sigma algebra, let's take real line with the Lebesgue sigma algebra. Okay, and you take this is 0, 1. So this is the diagonal. Inside that, I take this set. Okay, so let we had constructed a non-measurable set, right? Let S be a non-measurable set. So S is a non-measurable set in 0, 1. Okay, so it's not a Lebesgue measurable set in 0, 1. So what I do is I take here. So there is a set here T. What is T? T is the set of x comma x where x belongs to S. Okay, so I take a non-measurable set in one dimension and I put it on the diagonal, so to speak. I just rotate it and put it on the diagonal. So stretch it to the diagonal and put it there. Okay, so that's what it is. So T is not measurable actually. Okay, so it's not measurable even with Lebesgue sigma algebra in the 2 dimensions. So it is actually, sorry, no, that's not correct. What am I saying? Sorry, this is not correct. So I should take because it is actually measurable because it has 0 measure. I think I should take which is not a Boyle set. So maybe I should take here Boyle sigma algebra. Sorry. That S will be as before, but this will be Boyle sigma algebra. Take Boyle sigma algebra. Now you take the same. S is a non-measurable set. Let's take a measured set which is not even Lebesgue measurable and take T to be x comma x where x is in S. So this is not measurable in B product B, which by the way, I have not proved it, but it is in fact equal to Boyle sigma algebra of R2. But okay, let's leave that for a moment. That's not measurable. But you see any section Tx dot, what happens if I take any section is either a singleton or empty. On any vertical line, there is at most 1 point. Same with T dot y. Same thing. Either a singleton or so all these are measurable. So Tx dot T dot y are in the Boyle sigma algebra of R for all x, y. But all the sections are measurable, but the set is not measurable. So this is just to say that the converse statement is not true. But we are not saying that anyway. We are just saying that if the set is measurable in the product space, then its sections are measurable. And if a function is measurable on the product space, then its sections are measurable. Okay, any questions here? So let me put down a couple of more statements and then give all the proofs. So now we bring the measure in. This has no measure. This is just about the measurable structure. Now I bring in the measure. So now we have found that for each x, Ex dot is in G, right? So now look at the map. So let's look at x going to. So Ex dot is a set in G, right? So I can apply nu to that. So this is a mapping from x to real numbers, and I can take similarly y going to, if I look at e dot y, that is in f. E dot y is in f, so I can take mu of that. Okay, so not only is ex dot measurable for each x, if the measure of that set in the other measure, those will be measurable. That's the statement. These are measurable functions in the corresponding sigma algebras. This is here with f, here with g. Okay, so here with f and Boyle sigma algebra, and here with g and the Boyle sigma algebra. Okay, so the measures as the section varies. So in other words, so as x changes, the section changes. It can suddenly change quite a bit. Okay, so it can suddenly make a jump and all that. For example, if you take a rectangle, the section, so if you take a cross b, what is e sub x? If I take any x, if x is in a, it is b if x belongs to a. So if x belongs to a, then you get this entire piece which is b, and it is empty if x does not belong to a. So if you see as x crosses over the rectangle, it suddenly jumps from b to empty, and you can imagine more wild sets a and b, not intervals, where this ex suddenly changes, right? Looks, but we are saying that it's not so bad. The measure of those sets still may change widely, but not too widely. It's still a measurable function. X going to nu of ax and y going to mu of e dot y. So the corresponding thing for functions, now it should be clear, is with integrals. So, well, this is if e is measurable. Okay, so I should have said if e belongs to h, and here I should put the hypothesis if. So let me just make it here r plus. Okay. The reason is if it's non-negative, you don't have to ask is it integrable. So that's the only reason. I just make it non-negative. It's a non-negative measurable function. Then x going to the integral of f. So we saw that fx dot is a measurable function on y. So I can certainly integrate with respect to nu over y. Similarly, we can take the mapping y going from, so this is a mapping from x to r bar, and this is a mapping from y to r bar, which is y mapping to integral of, so f dot y is a measurable function, so I can integrate it with respect to mu over x. So these are measurable functions. Okay, so that is all. That is the lemma I wanted to say. Maybe take a look at it for a moment and see if things are clear, or should I explain something? So the statements, okay. I mean, said so they are not. None of them is actually difficult. So we'll just prove them now. So the proofs are, I mean, standard proofs. Maybe it is a good recap before your exams of the standard tricks of measure theory that we have seen before. So let's see the proofs. So for example, first one, let's see. If E is in H, then the sections are measurable. Why is that so? So anybody has a suggestion how I would prove this? If E is a measurable set in the product set, then the sections are measurable sets in the original spaces. Why is that true? Yeah, maybe I will wait for a suggestion from someone.
So maybe we could express E as a union of disjoint rectangles and then work with individual rectangles. For rectangles, that's going to be easy, right?
Okay, so you have said the correct wrong incorrect thing. So which I warned against many times. So it's not going to be a union of rectangles, but that should remind you what you should do. So
All
it's
right.
not true. It's a, so what is what that's precisely takes us back. What is the statement hypothesis? E is in H. What is H? H is the sigma algebra generated by rectangles. And that has no simple expression. Okay. What is sigma algebra generated by rectangles? It's the smallest sigma algebra containing all rectangles. Nothing more, nothing less.
Ah, yes. So just do the whole good set thing.
So look at all sets which have the property. Right? That's what you do. So you just take. So let what else? E, F, G, H are taken. So let's call it H naught. Be the set of all E such that Ex dot belongs to F. Sorry, Ex dot belongs to G for all X in X, and E dot Y belongs to F for all Y in Y. So you just look at all those E which have the property that you want. Now let's look at that collection and what does that collection tell me. So first of all, so H naught contains rectangles. Okay. Why? If E is A cross B, then Ex dot is either B or empty, right? I mean, I just now showed this. If X, this is if X belongs to A, then that section is that, and if X does not belong to A, it's empty. So in either case, it is measurable. Both are measurable because A cross B, where A is in F and B is in G, right? That's what it means. So it contains those rectangles. So similarly, E dot Y will be A or empty set. So it contains H naught contains rectangles is okay. So next, what do you want to show? H naught is a sigma algebra. Why is that so? Well, let's look at suppose E belongs to H naught. Let E belong to H naught. Does E complement belong to H naught? Well, E complement, what are the sections of E complement? I say it is nothing but Ex dot complement and similar for the other one. E complement, the Y section will be yeah, so the picture is sort of okay. Let me do another picture here. No, so let's take E is here. So if I take an X here, so Ex is essentially this vertical line. When so you have to project it to the Y part. But what is if I take E complement? I'm taking the entire outside and then taking the X section. What will that involve? It will involve this entire part of the line, vertical line, which is not here. That's the same as the complement of this part in the vertical line, right? So this is what I'm saying here. So that's all. So which implies that E complement belongs to H naught. Why? Because by assumption Ex dot belongs to G. So its complement belongs to G and E dot Y belongs to F. So its complement belongs to F. So that's all. And if you take ENs in H naught, then the claim is and E is the union of ENs, then Ex dot is just the union of all those sections. And E dot Y will be union of dot y. Okay. That is also clear. I mean, what is ex dot? Ex dot means all those y such that xy belongs to E. If xy belongs to E, then xy belongs to, the same as saying xy belongs to some En. That is same as again saying that y belongs to the x section of En and so on. So it's all trivial. So hence H naught is a sigma algebra. So we have proved that H naught is a sigma algebra. So these two together imply that H naught is actually equal to, so here I would have put E in H. In the definition, you take those elements of H which have that, and H naught is H. Because H is generated by algebra rectangles and it's a sigma algebra, so that's it. Is it clear? So this is how you do it. Any questions about this? So this is a standard trick that we have used before. So keep this in mind in the exam again. This is a common mistake that one can do in measure theory, but this is the way you argue. Because generated sigma algebra, you don't have an alternate description, internal one, you have an external one. Okay, let's next prove 2. Okay, 2 is actually trivial. Okay, 2 is nothing. 2 is also easy. So if f is a function from z to r bar, then fx dot is a function from y to r bar. Okay, so you remember that fx dot applied to y is just f applied to x comma y. Okay, so what I want to say is fx dot inverse of some set A. The Borel sigma algebra this side on the extended real numbers. So you take A in the Borel sigma algebra, then what is the inverse? It is all those y in capital Y such that fx dot of y belongs to A. But that is the same as all those y in Y such that f of xy belongs to A. Okay, so is it clear that it is the same as if I look at f inverse of A? F inverse of A is all those xy such that fxy belong to A, but I only take the y coordinate where I fix the x coordinate. So is the section of this. Fx dot the inverse images of the section of the function are just the sections of the inverse images of the original function. So this is anyway belongs to this, we know. So well, what I'm saying is f inverse of A belongs to H, and so this belongs to G, because we have shown that for any set in H the sections belong to G. Similarly, dot y. Okay, so that is okay. So let me do the third part. Maybe I will leave the fourth one because I don't know whether I'm running out of time or not. So third one is that these things are measured. Any questions about the first two parts? Okay, so sorry, there was some phone ringing. Yeah. So the third part, what is it? We now want to bring the measure in. Okay, so I will do 3 and I will leave 4. Okay, it's actually fairly. Okay, so x going to new x dot. Okay, so we want to look at. So how do we prove this? I mean, so you have to show that if E is in H, then this is measurable function. How do you show that? Any idea? So what is the idea? So it's the same idea, right? You should try the same. You should look at all E with this property. So again, you look at H naught with a set of all E which are in H such that X going to nu of Ex dot is measurable. Okay, I will just write this one. You can write the other one also, but just to reduce the writing, let me just take the first property. The same, absolutely the same applies to the second one. Y going to mu of Ey dot E dot Y. So let's just look at this one. So what I want to show is that this is the whole of H. So first of all, if E is a rectangle, so let's give it, if E is a rectangle, then what is nu of Ex dot? What is Ex dot? We have seen Ex dot. Ex dot is either B or empty set depending on whether X belongs to A or not. So I can write it as nu of B if X belongs to A and 0 if X does not belong to A. Which is, if you want to write it in with notation of indicators, it is nu of B times indicator A of X. Okay, is this a measurable function? Right, because indicator A is a set in F, so indicator A of X is a measurable function. So this is a measurable function. So it is simple. So this is actually, so H naught contains rectangles. I mean measurable rectangles, of course, A cross B with A in F and B in G. Now what do you do? How do you show H naught is equal to H? How do you show that? What do you try showing? So you try to show it's a sigma algebra, right? That's what you might want to do. But can you show it? I mean, can we show it is closed under complements and can we show it is closed under complements and unions? The problem with this is, you see the union, how will you show, what will you say about the, it is correct that Ex dot is the union of this, but this is not a disjoint union, right? So how will you show this? So this is actually okay if you take disjoint unions. Okay, but if you don't take disjoint unions, it is not clear. So what should you do in such a situation? So,
well, can we think of a disjointification of sorts?
okay, not always. I mean, so it is not so easy. So let's take, so this is one part. So now let us say, suppose ENs, so disjoint union means suppose ENs increase to E. I will just write it in this way so that, see, this is a part, this is something that has occurred before. The exact same problem has occurred before. That's why you should remember situations. So, and what got you out of those difficulties? This has occurred before when we wanted to show if two measures agree on an algebra, then they agree on the generated sigma algebra. Okay, so what did we use in such situations? So let me say what works. Okay, so countable unions is difficult. So if ENs increase to E, then EN X dot certainly increases to EX dot, right? I mean, that is not, I mean, all the sections will also be contained in one another because the set itself is contained and then they will increase to EX dot. This is easy. And nu of EX dot is the nu of, okay. Yeah, nu of EX dot, sorry, is the limit of nu of En X dot. So it's a limit of, these are measurable. Hence, this is a limit. So it is a measurable function, implies measurable function of x. Okay, because it's a limit of measurable functions. So this part is okay because it was increasing to e, this was fine. Also, let me say another thing, maybe this will jog your memory. Suppose, so okay, so this is fine, right? So this, okay, actually it's enough to do from here. So this is fine, but how do you do for countable unions? So what you have is that from this you can do for disjoint unions, because disjoint union, if I have some sets which are disjoint, then I can take the union of the first n of them to be En, so that will increase to the full union. And so it comes from here. So for disjoint unions, it's okay, but how do you do it for countable unions in general? So this is the kind of stuff you should remember if you want to be able to work with measures. So there is something, I mean, once you remember the idea, it takes few minutes or hours to work out the details, but however much you try, you will not be able to overcome this. If you try disjointifying and so on, you will not be able to do it. Not so easily. So what is a real nugget of idea that you have learned long ago? Yes. So let me say, so this shows H0 is a monotone class. It is closed under increasing unions. Okay, so sorry, what I wanted to say was if Ens belong to H0 for all n, then E belongs to H0. That's what I am arguing. If Ens belong to H0 for all n, then E belongs to H0. So H0 is a monotone class. So what is it then? What works? So the monotone class theorem, what does it say? So is it equal to H? So let me ask.
Monotone class generated by rectangles will be the sigma algebra, right?
Right, but why is that so? What does monotone class theorem say? The monotone class generated by a
Algebra, right?
Algebra, right?
rectangles don't form an algebra, but once H0 contains rectangles, it also implies that H0 contains the algebra generated by rectangles, right? Because what is in the algebra contained by H0 contains algebra generated by rectangles. It's not true in general, but here because remember, because this is all finite disjoint unions. Algebra elements are finite disjoint unions of rectangles. Therefore, the measure goes well under that. This is finite disjoint union, right? The measure is the sum of measures. That's important. So check this. Okay, so check this. I mean, there's not much to check, but be careful that you check actually what hypothesis you have and what conclusion you're drawing. So from rectangles, you get also for finite disjoint unions of rectangles, because measure goes well under disjoint unions, not under general unions. So it is already contains the algebra. Is a monotone class. So by monotone class theorem, H0 is equal to H. Okay, so that finishes the proof. That means for all E in H, this is true, and the other statement is almost an identical one. So it's you can now put that also in here or do it separately. Okay, so that proves 3. So we have proved 1, 2, and 3. Any questions about proof of 3? Is okay? Okay, so that leaves 4. I mean, okay, what is 4 first of all? The integrals of these things are measurable functions. Okay, so the integrals of the sections. Okay, so this is okay. So let me just write it very simply. It is actually easy. If f is a simple function, f is some alpha 1 indicator E1 plus alpha k indicator ek, then fx dot is integral fx dot d nu is what I took, right? So what is it that I am supposed to show? If you take the section of f and the vertical section and integrate with respect to nu, what function do I get? Fx dot d nu is going to be, first of all, fx dot is going to be just the alpha 1 indicator E1 section plus alpha k indicator ek section. Okay, so this will be just the alpha 1 nu of E1. Okay, so I have to write it bigger. Nu of E1 x dot plus alpha k nu of ek x dot, which is measurable. So this is a measurable function of x. By 3. Of course, each of the EIs are in H. That's what it means for f to be a simple measurable function. Okay, so this is true. So for simple functions, it is true. Now, if f is non-negative measurable, then find simple functions fn that increase to f almost surely. That we can do. I mean, you can do it pointwise. In fact, fn increases to f, let's say pointwise. You don't even need exceptions, but you can write almost surely. It doesn't matter, pointwise. Hence, then the sections also will increase. Okay, so if it is not clear, you go over this. I will just skip this. F x dot, and by monotone convergence theorem, integral fx dot d nu is the limit as n going to infinity of fn x dot d nu for all x. So it is the increasing limit. So as a pointwise limit of this is a measurable function. Because that's what we proved in the first part. For simple functions, this is a measurable function. So limit as measurable function, this will be measurable. Okay, so that's the end of the proof. Okay, so we spent some time doing the preliminary, but okay, once we do that, then we are in good shape. So we can now actually go back to the construction of the product measure. In fact, we'll understand something about the product measure also. But are there any questions about this? If you did not follow particular steps in the proof, you just postpone it and work it out later. The point is the function parts are actually, there is nothing much. It comes from the set conclusions. 1 and 3 are the key thing, and 1 and 3 involve the tricks in measure theory that we used before. One is the external definition of a generated sigma algebra as well as the monotone class theorem. These two are used in these tools. Okay, so now let's come to the construction of product measure. So the setting is always the same, so I will not write it again. So let's define. So I'll define two things. Okay. So define theta on H. Okay, so define theta from H to R plus by, how do I define theta of E? Okay, so E is some set, right? See, I want to define the product measure. So one way is the usual idea that we do, which is I take sections of it. So if I want to find the area of it, what I do is, this is the old idea of going back all the way to Archimedes, that if I want to find the area of this piece, then I cut it into pieces, and in each vertical line, I calculate the length. Or it need not be a line segment, it may be a union of line segments or a more complicated set. I take the length and then I integrate it over. So that is what we do. We take, for each vertical section, we calculate the measure. Okay. Nu of Ex dot. And then I integrate it over the X part with respect to the measure on the X variable. Okay. So now you see, I am using everything in the previous lemma to make sense of this. What am I doing? So for E in H, Ex dot is first of all in Ex dot is in G. So I can take nu of Ex dot, and then the function x going to nu of Ex dot is a measurable function. Therefore, it's a non-negative measurable function on X. So I can integrate it with respect to mu. Okay, so this is what we are doing. So maybe this is, as of now, let's write it as, but it's all actually, because mu and nu are finite, I don't need the extended real numbers, but it's fine. So this is well defined. So this is well defined by and finite by lemma, because nu of Ex dot is bounded by some, let's say the mass of nu is 1 and mass of mu is 1. This is at most 1, and this is integral of 1 is at most 1. So it's all finite. So we can also do it the other way. Instead of doing it like this, we could have used the horizontal sections, right? We could have done it the other way. Okay, so define tau from H to R plus by tau of E equal to integral over y mu of E dot y. Now I take a horizontal section that is a measurable set in X. So sorry, I write. And then integrate with respect to X. Okay, this is also well defined for exactly the same reason. So what is the point? So the claim now is that, theta and tau are actually measures. And for rectangles, they agree with what we want, mu of A times mu of B. So then, once you agree to this claim, so then what happens? So this implies that theta equal to tau, right? Because they agree on a pi system. Okay, they agree on this and sense also on the algebra. If you remember pi lambda theorem, this, so theta equal to tau because they agree on a generating pi system or algebra. So you can put it either way. If you do not remember pi lambda theorem and you don't remember what pi system are, go to algebra. If they agree on rectangles, they agree on the algebra generated by rectangles, because that's consists of finite disjoint unions. So for theta and tau agree on the algebra, so they have to agree on the sigma algebra. Okay, so that's the thing.
Sir,
And 1 second. Let me just
Yeah,
complete.
yeah, all right.
Okay. Theta equal to tau, and this is the product measure we wanted. Okay, just a point that this is the product measure because any other product measure also agrees with these on the rectangle, so it has to be this. So not only have we constructed the unique product measure, we have two different expressions for it. You can do it like this or like this. Okay, so go ahead with your question.
Well, so I wasn't entirely sure if we had discussed pi lambda theorem in class. Had we? If so, when?
Yeah, so then let's remove that. So monotone class theorem, I had mentioned, in fact, I had not discussed, I know what I had done, somehow I vaguely remember that I had mentioned that there is the pi lambda theorem, there is
Right.
also the monotone class theorem. These are equivalently usable. They are not the same theorem, they are equivalently usable. You just use the algebra part here if you like.
All right.
Okay.
Okay, sir. Thank you.
Yeah. So the pi lambda theorem tells you that if the lambda system generated by a pi system is the sigma algebra generated by the pi system. So that's the okay. Anyway, so it's not needed. You just use the algebra generated just like I did here. Once they agree on rectangles, they have to agree on the algebra. In fact, any two measures. So this is the uniqueness part of the product measure. Any two measures that agree on rectangles will have to agree on the algebra generated by rectangles. Sorry. So this concludes the uniqueness of the theorem. Okay. Not only uniqueness, now we have two expressions for the product measure like this. Now the only thing to prove is that this is a measure. Okay. Why this claim? Proof of the claim. Let's prove the claim. So let's look at enough to do for theta. Tau will be identical, right? The proof will be identical. So first of all, let's do the second part. So what is theta of A cross B? So if A is in F and B is in G, by definition, theta of A cross B is nu of Ex dot. So will be what is the X section of this set? It will be nu of B indicator A of X. Right? You remember that this is the X section of nu of Ex dot will be precisely this. I did it here somewhere in the proof, I think. Nu of Ex dot is the nu of B times indicator A of X. Okay. So that is, of course, nu of B comes out as a constant and you get nu of B times mu of A. So this proves the second part. That this is equal to this, we have proved. Now, why is theta a measure? So that theta is a measure is it's almost like the other theorem we had proved. It's not quite the same actually. There was a theorem we proved that you can integrate a function. I mean, okay, it's not quite that sort of one. Okay, so let's just do it properly. So this is because if all you have to show is countable additivity, right? Why is that? So let's say E is the disjoint union of ENs. This implies that the X sections are actually disjoint unions of the X sections here. Because the X coordinate is anyway common. If something was common here, then that point, that X comma Y would be a common point to two different ENs. So this is true for all X. So what this implies is that nu of Ex dot is the sum of nu of En X dot. Okay, over n equals 1 to infinity. So what is the integral of this? By monotone convergence theorem, theta of E, which is the integral of nu of Ex dot d mu of x over x. This is the sum. This is where the MCT is being used. It's a sum of these measurable functions and all are non-negative. So you'll get that this is the sum of integral mu of En x dot d mu of x, which is same as sum over n theta of En. Okay, so you show that this is a measure. So this completes the proof of the claim. There is nothing more to measure except countable additivity for disjoint countable union of sets. So this proves the existence and uniqueness of the product measure. So that finishes that. Any questions here? I have 10 minutes. There's one theorem to do, and that will be the end of it. But before that, any questions about? We have shown the existence and uniqueness of the product measure and two expressions for it, which are exceedingly useful. This is how you actually work with things. You slice it in horizontal or vertical pieces and calculate, right? So that's how you do it. Okay, what else is left? It is again, everything, it's a recurring theme in analysis that what you write for sets, you can write for functions and vice versa. Sometimes the statements will be slightly different, but it is a general theme. Any statement for sets, there will be an analogous thing for functions and vice versa, like 1 to 2 or 3 to 4. Similarly, the idea that we can find the product measure of a set by making sections and then calculating measures of sections and integrating with respect to the other one, either like vertical or horizontal sections. What is the analogous statement for functions? That is called Fubini's theorem. Okay, so that is the last thing that I will say. So this is called Fubini-Tonelli theorem. So first one, this is the Tonelli part. This is the, suppose f is as everything is as before, but f is a non-negative measurable function. Okay, by the way, this uniqueness, so this one is denoted mu direct product nu, as I indicated. So actually I should have written here. So we have shown existence and uniqueness of mu tensor nu, which is also equal to theta, which is also equal to tau. Okay, that's the same other expressions. So we think of product measure as existing and as these as two different ways of calculating the product measure. Okay, so if f is non-negative measurable, then integral over z f d mu tensor nu, the product measure, is actually the same as integrate, first fix x in y and you do fx d nu and then integrate this with respect to d mu of x. But it is also equal to, you can do it first over y and next over x. So this is fx dot, or you can do f dot y, which is a function on x. You can integrate with respect to mu and then you integrate with respect to d nu of y. So this is the statement. Okay. So here you see actually one of the small points is that, so earlier when defining integral, we had this notation for integral with respect to a measure, but I also said we can write a dummy variable. Okay, so it seemed completely redundant and confusing to introduce unnecessary variables like this, but I challenge you to write Fubini's theorem without using a dummy variable. Okay, so it is going to be a pain. So that's why it is actually useful to write it like that. In fact, it is the cleanest is to, I mean, the most easy to remember way is to just write fxy d this of xy is equal to over z is equal to f of xy d mu of y d mu of x, etc. So this is the usual way we write it, and it's easy to remember instead of writing the sections, because this is fx dot of y means f of xy d nu of y. That's how you write it. Okay. So, but let me state the second part is the same thing for, but not for non-negative functions. But what is the hypothesis? We assume is integrable with respect to mu tensor nu. Then fx dot is integrable with respect to nu for almost every x. Okay, so fx dot d nu, this integral will make sense. It's integrable for almost every x, and x going to fx dot d nu over y is integrable with respect to mu, and the integral of f with respect to, the statement is exactly the same. It is the hypothesis that one should pay attention to here when you go to the integrable part. The hypothesis is exactly, I mean, the conclusion is exactly the same. You can integrate the sections with respect to nu, and then you integrate with respect to mu. But you have to make the appropriate noises before writing integrals, because you don't know whether the integrals exist. So you have to say the inner integral exists, but that you don't need for every x, but for almost every x. Almost every with respect to what? With respect to the measure mu. And then you have a function of x. For all those x for which you can define the integral, you have this value. You take that as a function of x, that is also integrable with respect to mu, and you integrate that with respect to mu. You get back this cell. And similarly with f dot y, which I will write, right? And finally, this will also be equal to integral over y, integral over x. So you do f dot y d mu, and then you integrate with respect to mu of x. Okay. So this is all there is to it, Fubini's theorem. But the most common mistake done in Fubini's theorem is to not pay attention to the hypothesis. If it's non-negative, don't worry. You can always interchange integrals. If it is non-negative, all these three things are well defined, possibly infinity, but they are all equal. But many times what mistake people make is, if f is in, the hypothesis is f should be integrable in the product measure. But many a time what people make the mistake is they separately check one of these iterated integrals exists. They forget this, you just take this one. Suppose this entire thing is true, fx dot is integrable for every x and this is integrable. So then you can calculate this quantity. And suppose the same is true with y and x interchange. So f dot y is integrable and this is true. Both of these iterated integrals may exist, but they may not be equal. Easy to provide counterexamples, but it's often people forget and make a misapplication. You have to first check the integrability in the product measure. Then you can do this. Okay, so it's not too, you don't have hypothesis in terms of the individual integrals, which guarantee that sort of thing. Okay, so well, okay, the proof is actually somewhat simple. I'll just provide you the proof of one. Two follows from one fairly easily. But so let me just give you the proof of one. It is quite simple. So if f is indicator of some E in H, then what is integral f is just the E. And what is the?
It's 5 o'clock.
What is the integral over x, integral over y, fx dot d mu of x? This is exactly integral over x nu of ex dot d mu of x, which is what we call theta of E. And the other one, integral over y, integral over x, f dot y d mu integrated over nu of x, nu of y is actually the same as the other one, the mu of E dot y d nu of y, which is tau of E. And so we have shown all these are equal. So this is true when f is indicator, hence statement true. F simple measurable, because that will be a sum of such things, linear combination of such things, and hence for F non-negative measurable. How do you do that? By monotone convergence theorem. So you can find always simple functions increasing to your non-negative measurable function and use monotone convergence theorem in each of these things. Fn's will increase to f, all the sections will also increase to the corresponding f, and then the integrals will also increase to the corresponding integral. So I will just leave out the details and say that it's done. And the second part is fairly straightforward from the first one. So you can look it up in the book or notes, which I will put up later. Okay. So that ends the Fubini's theorem. This is pretty much what one wanted to show here. Okay. It's a very useful theorem. It's a very powerful theorem. What I did not do in this lecture is give any examples or any uses. Maybe in some practice problems there will be some. Okay. Okay. So that finishes the course also. So yeah, as Shekhar had said the other day, maybe I will put up some lectures on the extra parts I didn't cover, but completely ignorable for the purpose of the course and the exams. Okay. Okay. So I will stop here. Any questions or etc. we can